we've taken a look at several different ways that we can actually utilize redox reactions to our own benefit. We took a look at electrochemical cells that use electrochemistry to actually create electricity. We've taken a look at electrolytic cells that we can use to split a compound into separate elements, or even to coat the surface of a metal with another metal to protect it. But another thing that we can have happen with a redox reaction is some reactions that we don't actually want to take place. And a really good example of this is corrosion. Corrosion is basically the oxidation of metals, and in some metals, it's pretty harmless. You see this with things like aluminum foil, or any aluminum of any kind is coated with an oxide layer that really actually protects it. Whereas some substances like iron, their oxidation and their corrosion becomes really detrimental, turning them into a substance that totally changes their chemical properties and physical properties to make them really unusable. And what I wanted to do here is show you how that corrosion of iron actually takes place. So when you have a piece of iron and it's undergoing corrosion, the first thing is it needs to be exposed to the atmosphere or to oxygen. The other thing that needs to happen is there needs to be water, because water is also one of the reactants in this, and you do end up with some aqueous products. This is why keeping things really dry will help protect against corrosion, but it is extremely difficult. Keep in mind, there's actually water in the atmosphere, and that water can actually react and cause this to take place. What's going to happen over the course of this reaction is we are actually going to have oxygen that's in the atmosphere. It essentially dissolves in the water, and when the oxygen and the water come to the surface of the iron, the electrons that are in the iron are actually going to be given away. Those electrons in the iron are going to be taken by the oxygen and the water, and this is my water. Those are going to combine together, and in the process, they are actually going to produce hydroxide molecules. Now, the only thing here is this electron has to come from somewhere, and the electrons are coming from the surface of the iron. And as the iron gives away its electrons, it actually becomes aqueous in the form of Fe2+. This Fe2+ can then actually react with the OH- to produce Fe3, or sorry, FeOH2. This will then undergo some more chemical reactions later, but let's actually take a look at the reactions that are happening in the case of the corrosion. So the oxygen reaction is that the oxygen is going to react with water. It is going to gain electrons as it is reduced and turned into hydroxide ions. This is the reduction reaction. The oxygen actually reducing into OH-. The oxidation reaction, on the other hand, starts with our Fe as a solid, and it is actually going to turn into Fe2+. Now, to balance the electrons, because of the 4 electrons here, we have to make sure we have 2 irons being exchanged, each iron losing 2 electrons. These electrons that get lost by the iron end up being given away to the oxygen, and this is our oxidation reaction. If you were to take a look at the actual values for these two reactions in terms of their voltage, the electromotive force, or the voltage for this first reaction is 0.40 volts, whereas our other reaction over here, the iron being oxidized, well, that one is 0.44 volts as an oxidation reaction. If we wanted to figure out the actual voltage of this reaction, we could just add those two values together. So we could just take our reduction, add it to our oxidation. Remember, I flipped the oxidation, which changed the sign here. I just did that ahead of time. and you end up with 0.40 volts added to 0.44 volts, and you find that this cell actually has a positive 0.84 volt value. What this really means is this is spontaneous. Because we have that positive value for our voltage being produced, we get a spontaneous chemical reaction. So as long as you have iron metal being exposed to water and oxygen, you actually will have a spontaneous corrosion reaction. As I said previously, some spontaneous corrosion reactions just produce a layer that actually sticks to the surface of that metal. This is something we see in materials like copper or zinc or aluminum, which means that they don't really fall apart as they corrode. But for iron, it's a much bigger deal because of the way that it actually corrodes. You see, as iron corrodes, it gets pitted, meaning that the actual iron oxide, the final product of a series of reactions, so essentially that FeOH2 is going to undergo a series of reactions and finally become Fe2O3, the material we think of as rust. And that rust will actually form in flakes, which then chip off of the surface of the metal. This actually exposes more surface area, which means it will spread throughout the inside of the metal. And as that corrosion starts spreading, it actually exposes even more surface area, which will cause even greater pieces to start breaking off, and you end up with a sped up corrosion over time because of the greater surface area that starts to be exposed. This is a huge problem when dealing with the corrosion of iron. Because iron corrodes so easily and has so many problems, people eventually figured out ways that they could actually work with it to protect it from corrosion. And that's what we're going to take a look at in our next video. So thanks for watching.